Have you ever, stopped to wonder why that steaming hot cup of coffee always cools down, always settles at room temperature, but never spontaneously heats itself back up? Or how about a giant airplane? Hundreds of tons of metal just soaring through the sky. How does that work? Or even something really basic like why you feel hungry, or how your body just sort of keeps itself at that steady temperature. Well, the answers to these things, these seemingly simple but actually really profound questions, they all point back to one foundational science. Welcome to the Deep Dive. Today we're plunging headfirst into the fascinating world of thermodynamics. And this isn't just, dry formulas. It's the science of energy itself, how it interacts with literally everything. Our mission for you, listening in, is to explore its core concepts, its kind of unique language, and the essential measurements, stuff that underpins everything from your lunch to, well, rocket science. We want you to quickly grasp these vital nuggets, connect the dots, maybe have some real aha moments, without getting totally overwhelmed. So, okay, thermodynamics. If we're going to dive in, we have to start at the beginning. It's the science of energy, right? But what is energy? Really? How do we even start thinking about that scientifically?
That's the perfect place to start, actually, because energy is precisely what thermodynamics is built on. Fundamentally, you can think of energy as just the ability to cause changes. It's that potential or maybe active force that makes things happen. And what's really cool, if you look at the word itself, thermodynamics, it comes from the Greek therme for heat and dynamis for power.
Heat and power. Oh, wow.
Yeah, so that tells you a lot about its early days, right?
Yeah.
It's all about converting heat into useful power. Think Industrial Revolution, steam engines. But now today, the scope is just huge. It covers all forms of energy, all its transformations, power generation, sure, but also refrigeration, even just the subtle ways properties of matter relate to each other.
And right at the heart of it all are these fundamental laws. And they're not just abstract ideas, are they? They really shape our everyday world, like the conservation of energy principle, also known as the first law of thermodynamics. I always remember it as energy can't be created or destroyed, only changed. Is that basically it?
That's the core idea, absolutely. Spot on. The first law says the total amount of energy in any system stays constant. It just transforms. Think about a rock sitting on top of a cliff. It has potential energy.
Right, potential.
Then it falls. That potential energy converts into kinetic energy, the energy of motion. But the total energy is still the same, conserved. Or maybe closer to home, think about your body, what you eat. The entire diet industry really runs on this principle.
How so?
Well, if the energy you take in from food, your energy input is more than the energy you use up through activity, your output. Your body stores the extra. It has to go somewhere.
Oh, okay.
It's all about that balance. Energy in minus energy out equals the change in your body's stored energy, I in out in Steiner E. Simple but profound.
Okay, that makes sense. Energy is always there, just changing its form, like changing clothes.
Yeah.
But here's something that always gets me. If energy is conserved, why does my phone battery die? Like, where does that energy go if it's not destroyed? And back to the coffee cup, why does it cool down, but never heat back up on its own? It feels like some things only go one way.
That is a brilliant question, and it takes us right into the second law of thermodynamics. You've hit on something crucial. While the first law is about the quantity of energy, it's always conserved. The second law introduces the idea of energy quality.
Quality, okay.
Yeah, it tells us that real-world processes, the stuff we actually see happen, always occur in the direction of decreasing energy quality. Your hot coffee cooling down. Perfect example. The high temperature energy, the useful high quality energy in the coffee, it degrades. It spreads out into the cooler air as less useful, lower quality heat.
So the energy's still there.
Still there, yeah. Conserved. Just diffused into the room. But its ability to do useful work, its quality, has dropped. You can't just gather all that low-grade heat back up and spontaneously reheat the coffee. The process naturally goes towards lower quality energy.
Wow, okay, that's a genuine aha moment.
Yeah.
Quantity versus quality, that explains so much. What's kind of amazing, though, is that these laws, they're fundamental, right? They've governed the universe forever.
Yeah.
But thermodynamics as a formal science, it's actually pretty recent. It really only took off after people like Thomas Savery and Thomas Newcomen built those first working steam engines back in, the early 1700s.
Exactly. It's a classic case of practical invention driving scientific understanding. It's quite something that both the first and second laws really emerged around the same time in the 1850s. That was thanks to people like William Rankine, Rudolf Clausius, Lord Kelvin. In fact, Kelvin himself coined the term thermodynamics in 1849.
Just like that.
And the first textbook on the subject came out just 10 years later, 1859, written by Rankine. Now, when we talk about doing thermodynamics, there's sort of two main viewpoints. For most practical engineering stuff, we use classical thermodynamics. Macroscopic,
Microscopic, meaning?
meaning we look at the substance as a whole, bulk properties, like measuring pressure with a regular gauge. We don't worry about individual molecules. Then there's statistical thermodynamics, microscopic. That dives into the average behavior of all the individual particles. Super insightful for understanding why things happen at a tiny level, but honestly, for most engineering problems you'll run into, classical is usually perfectly fine, more than sufficient.
Okay, so let's bring it back to the listener. What does this all mean for you? Because I know it can sound a bit abstract, maybe just for engineers, but the truth is thermodynamics is everywhere. It's
Yeah.
woven into everything. Your own body, it's this incredible thermodynamic machine. Your heart's pumping blood, that's work. Your cells are constantly converting energy. You're always giving off heat to stay at the right temperature. Even just feeling comfortable, not too hot, not too cold, that's thermodynamics at play. And look around your house. The stove, heating, AC, the fridge, pressure cooker, water heater, even your computer and TV, they all run on these principles.
Absolutely. And then you scale up. Think about car engines, rockets, jet engines flying us around the world, huge power plants generating electricity, solar panels soaking up the sun. Even the way we design energy-efficient buildings now, it all comes back to these fundamental thermodynamic ideas. It's foundational science, truly impacting almost everything, often without us even noticing.
Okay, like any science, thermo has its own language. And if we want to really get into this deep dive, we need to speak it correctly. That brings us to dimensions and units. What's the actual difference? Sounds a bit technical.
It's a really important distinction, though, for clarity. Dimensions are the fundamental physical quantities themselves. Things like mass, length, time, temperature, the basic concepts. Units are the specific magnitudes we assign to those dimensions. So mass is a dimension, but kilogram or pound are units we use to measure it.
Got it. Dimension is the what, unit is the how much.
And speaking of units, we seem stuck with two big systems, don't we? The English system, which honestly always feels kind of random to me, and the metric SI system. I mean, 12 inches in a foot, 5,280 feet in a mile, it just seems designed to be confusing.
You're definitely not alone in feeling that.
Yeah.
The English system, or U.S. customary system, USCS, it does have all those arbitrary relationships, makes conversions a real pain sometimes. SI, the international system, is the logical one, decimal-based. Simple. It's used by basically every other industrialized nation, including England, ironically enough. Right.
The U.S. is really the only one that hasn't fully switched over. We're kind of this dual system society, which adds its own layer of complexity.
I mean, here's something that really blew my mind when I first dug into this. The definitions of these basic units, they've actually changed quite a bit over time. There were some massive changes just recently. It goes way back. Systematic efforts started in France, like 1790, trying to create a universal system.
And that whole historical journey led to this huge shift in 2018. Fundamental SI units got redefined big time. They're no longer based on physical objects, but on fixed values of universal constants. Take the kilogram.
Yeah.
It used to be defined by an actual chunk of metal, le grand K, kept in a vault near Paris.
Seriously, a physical object.
Yep, but now, it's defined by fixing the numerical value of the Planck constant, something fundamental from quantum mechanics. Same kind of thing for the meter. Used to be tied to the Earth's size. Now it's defined by how far light travels in a vacuum in a tiny fraction of a second. And the Kelvin for temperature, the ampere for current, the mole for amount of substance, all redefined based on fixing fundamental constants like the Boltzmann constant, elementary charge, and Avogadro's constant.
Wow.
This new way gives us this incredibly precise universal measurement system. It's not tied to any specific substance or physical artifact anymore. It's built into the laws of physics.
That's amazing. So the kilogram isn't even a thing anymore. It's a number based on physics.
Yeah.
Wild. And speaking of Kelvin, I've noticed some specific rules about writing SI units. Like, it's just K for Kelvin, not K, right? Why is that?
Yeah, that's just a convention for consistency in science. For absolute temperature scales like Kelvin, you just use the capital letter, no degree symbol. Same idea for force. The unit is Newton, lowercase when spelled out, but the abbreviation N is capitalized. And plurals, you'd say 5 meters, but the abbreviation is always 5 meters, never 5 meters. Little rules, but they keep things clear globally.
Okay, let's tackle some common mix-ups, especially for those of us living in this dual system world. The big one I always hear is mass versus weight. They are not the same kind.
Absolutely not. And it's super important in thermodynamics to get this right. Mass is how much stuff is in an object. It's inherent, constant. Your mass is the same whether you're on Earth or the moon.
Okay, constant stuff.
Weight, though, is the gravitational force pulling on that mass. And that changes depending on gravity. On the moon, your weight is about 1/6 of your Earth weight because the moon's gravity is weaker. But your mass, exactly the same.
Right, less pull, less weight.
The confusion comes from the English system using pound for both. You have pound mass, a PM, and pound force, pound BF. Now, it just so happens that 1 pound weighs 1 pound here on Earth at sea level, which makes it easy to mix them up. But they are fundamentally different concepts.
So pound is a force, pound is mass.
Exactly. To give you a feel, a force of 1 Newton, the SI unit, is roughly the weight of a small apple. A pound force, 1 pound, is more like the weight of 4 medium apples, much bigger force. And for energy, we use joules, which is a Newton meter NEM in SI, and often B2 British thermal units in the English system.
Gotcha. Okay, another one that often trips people up, power versus energy. I've definitely heard people talk about wind turbines generating like kilowatts per year, and it always sounds off. Can you clear that up?
That's a fantastic one to clarify because it's a really common mistake and it actually matters a lot. Power is the rate at which energy is used or generated. Think of it like speed. Its units are things like watts, W, or kilowatts, kW. Energy is the total amount used or generated over a period of time. Think of it like distance traveled. Units are often kilowatt hours, that's what's on your electricity bill.
Rate versus total amount.
Exactly. So saying a wind turbine generates 50 kilowatts per year is meaningless. Kilowatts is already a rate. It's like saying a car travels 60 miles per hour per day.
Right. Doesn't make sense.
A correct statement would be something like, this wind turbine with a rated power of 50 kilowatts is expected to generate 120,000 kilowatt-hours of electricity per year. See the difference? Power is the capacity. Energy is the total output over time.
Okay, that clears it up completely. Power is the how fast, energy is the how much. Like speed versus distance. Makes perfect sense. And this all leads to a really handy principle in engineering, dimensional homogeneity. Sounds fancy, but it's basically common sense, right? And a great way to check your work.
It's incredibly simple, yet so powerful. Dimensional homogeneity just means every single term you add or subtract in an equation must have the same units. You can't add kilograms to seconds, right? Apples and oranges.
No.
So if you're working through a problem and you find yourself trying to add, say, pressure, pascals, to velocity, meters per second, you know immediately you've gone wrong somewhere. Either the equation is wrong or you made a mistake setting it up. It's like a built-in error detector. Really useful.
Okay, as we start looking at specific thermodynamic problems, we need a clear way to define what we're actually studying. This brings us to these basic ideas: the system, its surroundings, and the boundary between them. How do we define those if I'm looking at, say, my morning coffee cooling down?
Good example. The system is just whatever piece of the universe you want to focus on. In this case, it would be the coffee itself, inside the mug. Everything else, the mug, the air in the room, the table, that's the surroundings. And the boundary is the surface that separates the coffee from everything else. It could be the inner surface of the mug and the top surface of the coffee exposed to the air. Boundaries can be real surfaces or imaginary ones we draw for analysis. They can be fixed or they can move, like a piston head. And importantly, we consider them to have zero thickness.
Okay, coffee is the system. Everything else is surroundings. Boundary in between. Simple enough.
Now, we split systems into 2 main types, closed or open. A closed system, sometimes called a control mass, has a fixed amount of mass. Mass cannot get in or out across the boundary. But energy can cross as heat or work. Think of gas sealed inside a piston cylinder device. The amount of gas stays the same, but you can heat it up or let it expand and do work.
Right, the stuff inside stays inside.
An open system, often called a control volume, is different. It's usually a specific region in space, like a pump or a turbine or your water heater. Both mass and energy can cross the boundary of an open system. Water flows into your heater, gets heated, energy in, and hot water flows out.
So my coffee mug, assuming no lid and steam can escape, that's actually an open system because mass steam is leaving.
Technically, yes, if mass is crossing the boundary. If you put a perfectly sealed lid on it, then it would be a closed system because only heat could escape through the mug walls and lid. Good distinction.
Okay. Now, any characteristic of a system, you call it a property. Things like pressure, temperature, volume, mass. But you make a distinction between properties that depend on the sides of the system and those that don't, right?
Exactly. We distinguish between intensive and extensive properties. Intensive properties are independent of the system's mass or size. Think temperature, pressure, density. If you take a swimming pool full of water and scoop out a cup, the temperature and density of the water in the cup are the same as in the pool.
Doesn't matter how much you have.
Right. Extensive properties, on the other hand, do depend on the size or extent of the system: total mass, total volume, total energy. These would all be smaller for the cup of water than for the whole pool. They scale with the size. A quick test is to imagine dividing the system in half. Do the properties of each half stay the same? If yes, it's intensive, like temperature. If the properties are halved, it's extensive, like mass.
That's a handy trick, divide in half.
Mhm.
Okay. But I've always wondered, especially with gases, molecules are flying around pretty far apart. How can we even talk about properties like density at a specific point? It feels like there should be gaps.
That's a really insightful question. It leads us to the continuum idealization. Even though matter is made of discrete molecules with space between them for almost all engineering purposes, we can treat substances as if they were continuous, smooth distributions of matter. No holes. A continuum.
Like, can we get away with that?
Because the number of molecules, even in a tiny volume, is just astronomical. Take 1 cubic millimeter of oxygen at standard conditions, that's like the size of a pinhead. It contains something like 3 times 10 to the 16th molecules.
Wow. Okay.
A lot. A huge number. So even on that tiny scale, the average properties like density are well-defined and very smoothly. This continuum model only really breaks down in extreme cases, like in a very high vacuum or way up in the upper atmosphere where molecules are genuinely far apart. But for most things we deal with, continuum works great. And building on that, let's quickly hit a few key fluid properties. Density, that's just mass per unit volume, kg/mi. Its inverse is specific volume, volume per unit mass, kg/mi. Then there's specific gravity, sometimes called relative density. It's super useful. It's just the ratio of a substance's density to the density of water at a standard temperature, usually 4 degrees C, where water is densest, about 1,000 kilometer.
So it's a comparison to water.
Exactly. Mercury, for example, has a specific gravity of about 13.6. That means it's 13.6 times denser than water. That's why it sinks like a stone, and why it's useful in barometers. Wood, with a specific gravity less than 1, floats. And finally, there's specific weight, which is weight per unit volume. Remember, weight depends on gravity, so specific weight does too, unlike density.
Okay, let's shift focus a bit. We've defined systems and properties. Now, how do we talk about the condition of a system and how it changes? We use the term state, right? What does that mean precisely?
A state is essentially the system's complete condition at a given moment. It's fully described by its properties. If you know all the properties, pressure, temperature, volume, etc., you know the state. And if even one property changes, the system moves to a different state. Thermodynamics often focuses on equilibrium states. Equilibrium means balance. A state where there are no unbalanced forces or potentials driving change within the system. It's sort of a settled condition.
Wonderful.
And there are different kinds of equilibrium. Thermal equilibrium means the temperature is uniform throughout. No hot spots or cold spots driving heat flow. Mechanical equilibrium means the pressure is uniform and not changing over time. Phase equilibrium applies when you have multiple phases, like ice and water. It means the amount of each phase isn't changing. And chemical equilibrium means no chemical reactions are occurring. For a system to be in full thermodynamic equilibrium, all of these must be true simultaneously. It has to be thermally, mechanically, phase, and chemically balanced.
Okay, that makes sense. And here's something I found really cool, almost like a shortcut. The state postulate. It says for many systems, you don't need to know all the properties to define the state. Is that right?
That's exactly right. It's incredibly powerful. The state postulate says that for a simple compressible system, which basically means a system where things like electrical, magnetic, gravitational effects aren't significant, just pressure volume work, its state is completely specified by just 2 independent intensive properties.
Only 2. That seems too simple.
It does, but it works. Now, the key words are independent and intensive. We know intensive properties don't depend on size, like temperature, pressure, density. Independent means you can vary one property while holding the other constant. For example, temperature and specific volume, volume per unit mass, are always independent for a simple substance. You can heat a gas, change T, without changing its specific volume if it's in a rigid tank, or compress it, change V, without changing T if you cool it just right.
Okay, T and V are independent. What about temperature and pressure? They seem pretty fundamental.
Good question. Temperature and pressure are usually independent, but not always. Specifically, they become dependent during a phase change, like boiling or condensation. Think about boiling water. At sea level atmospheric pressure, water boils at 100 degrees C. If you go up a mountain, the pressure is lower, and water boils at a lower temperature, maybe 90 degrees C. While it's boiling, if you know the pressure, you automatically know the boiling temperature, and vice versa. They're linked. You can't change one without the other changing in a specific way. So during that phase change, T and P are not independent. You'd need one of them plus another independent property, like specific volume, to define the state of the mixture of liquid and vapor.
Wow, okay, that's a subtle but really important distinction. So you need two independent intensive properties. Got it.
And any change a system undergoes from one equilibrium state to another, we call that a process. The specific series of states it passes through during that change is called the path of the process. Now, a really important idealized process in thermodynamics is the quasi-static or quasi-equilibrium process.
Quasi-static.
It means almost static. The process happens so incredibly slowly that the system remains infinitesimally close to being in equilibrium at every single step along the way. Imagine compressing gas in a piston so slowly that the pressure and temperature are always perfectly uniform throughout the cylinder.
Okay, like super, super slow motion. Why is that important?
It's important for two main reasons. First, they're easier to analyze because the system's state is well-defined at every instant. Second, real work-producing devices, like engines, deliver their maximum possible work when they operate closest to this idealized quasi-equilibrium condition. Friction and rapid changes reduce efficiency.
Makes sense. We also hear those ISO prefixes a lot when talking about processes. Can you quickly run through those?
Sure. Isothermal means constant temperature throughout the process. Isobaric means constant pressure. And isochoric, or sometimes isometric, means constant specific volume, like heating a gas in a rigid sealed container. And if a system goes through a series of processes but ends up back in its original starting state, that whole sequence is called a cycle. Think of the repeating processes in an engine cylinder or a refrigeration loop.
Right. Cycles are key for engines and fridges.
Exactly. And one more important type. Steady flow processes. These are common in open systems, like turbines or pumps operating continuously. In steady flow, the fluid properties might change from point to point within the device, like pressure dropping across the turbine. But at any single fixed point, the properties, temperature, pressure, velocity, remain constant over time. The flow is steady, not changing moment to moment at any given location.
Okay, steady flow for things running continuously. Got it. Now, let's talk about something we experience constantly, but is actually tricky to define. Temperature. We say hot or cold, but our sense of touch can be really misleading, can't it? Like on a cold day, a metal bench feels way colder than a wooden one, even if they're the exact same temperature. Why is that?
You're right. Our senses judge the rate of heat transfer, not temperature directly. Metal conducts heat away from your hand much faster than wood, so it feels colder, even at the same actual temperature. Defining temperature formally relies on the fact that some properties of materials change predictably with temperature. That's how a thermometer works, the expansion of mercury or the resistance of a wire. And this leads us to another fundamental law, maybe the most basic one, the zeroth law of thermodynamics.
Zeroth. Why zeroth?
Good question. It was actually formulated after the first and second laws were established, but it's so fundamental to the concept of temperature that it logically comes before them. So they called it the zeroth law.
Okay, so what does it say?
It sounds almost trivial, but it's profound. It says, if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other.
If A equals C and B equals C, then A equals B. Kind of like that.
Exactly like that, but for thermal equilibrium. The third body is key. That's your thermometer. If the thermometer reads the same temperature when touching body A and body B, then A and B must be at the same temperature, even if they never touch each other directly. It's the entire basis for being able to measure temperature reliably.
Ah, the thermometer's the third body. That makes sense. Okay, so we have scales for measuring this. Celsius and Fahrenheit are the common ones.
Right. Based on the freezing, 0 degrees C, 32 degrees, and boiling, 100 degrees C, 212 degrees of air, points of water at standard atmospheric pressure. Useful everyday scales. But in thermodynamics, especially when doing calculations involving fundamental laws, we almost always need to use absolute temperature scales. In SI, that's the Kelvin K scale, named after Lord Kelvin. 0 Kelvin is absolute zero, the theoretical lowest possible temperature. That's negative 273.15 degrees C. There are no negative numbers on the Kelvin scale. In the English system, the absolute scale is Rankine, R. 0 Rankine is also absolute zero.
Okay, Kelvin and Rankine for absolute temperature. Here's something I found really useful. The size of 1 degree Celsius is the same as the size of 1 Kelvin, right? And 1 degree Fahrenheit is the same size as 1 Rankine.
Exactly right. The increments are the same size. So a temperature difference or change of, say, 10 degrees Celsius is exactly equal to a temperature difference of 10 kelvins. Same for Fahrenheit and Rankine.
That's super helpful for calculations involving temperature changes.
It is, but, and this is a critical point for anyone doing thermal calculations, whenever a thermodynamic relation involves temperature directly, not just a difference, you must use the absolute temperature scale, either Kelvin or Rankine. Using Celsius or Fahrenheit directly in most thermodynamic equations will give you the wrong answer, period.
So when in doubt.
When in doubt, always convert to Kelvin or Rankine if you're stuck in the English system. It's virtually always correct to use K, whereas using degrees C can often be wrong. It's that fundamental.
Got it. Always use absolute temperature for the calculations.
Yeah.
Okay, let's move on to another invisible force that's all around us, pressure. How do we define that scientifically?
Pressure is simply the force exerted by a fluid, like air or water, perpendicular to a surface, divided by the area of that surface, force per unit area. The SI unit is newtons per square meter, and MMM, which gets its own name, the Pascal.
Pascal, okay.
Since 1 Pascal is a very small pressure, we often use kilopascals, kPa. Thousands of pascals, or even megapascals, MPa, millions of pascals. You also hear about bar. 1 bar is 100 kPa, pretty close to atmospheric pressure, standard atmosphere, 80 mm. And of course, in the English system, pounds force per square inch, PS.
And the idea of force per area explains things like why snowshoes work, right? Spread the force over a bigger area, less pressure.
Exactly. Same reason a sharp knife cuts easily. It concentrates the force onto a tiny area, creating very high pressure. Now, it's also really important to distinguish between different types of pressure measurements. Absolute pressure is the true pressure measured relative to a perfect vacuum, which is absolute zero pressure. But most pressure gauges we use, like a tire gauge, are actually calibrated to read zero when they're just open to the atmosphere.
Right, my tire gauge reads 0 before I connect it.
Exactly. So the pressure it reads when connected is called gauge pressure. It's the difference between the absolute pressure inside the tire and the local atmospheric pressure outside. Absolute pressure equals gauge pressure plus atmospheric pressure. And if the pressure is below atmospheric pressure, we call that vacuum pressure. It's how much lower the pressure is than the surrounding atmosphere.
So when my tire reads, say, 32 psi, that's 32 psi above atmospheric pressure.
Precisely. That's 32 psa, G for gauge. The absolute pressure inside is 32 psi plus whatever the local atmospheric pressure is, which is typically around 14.7 psi at sea level.
Okay, absolute gauge vacuum. Got it. Now, pressure in a fluid, it doesn't change sideways, but it definitely changes as you go deeper, doesn't it? Like diving in a pool.
That's right. Pressure in a static fluid increases with depth. For a liquid, the pressure increase is directly proportional to the depth, h, the density of the fluid, or paburo, and the acceleration due to gravity, g. The pressure at depth h is Pm plus rho absolute pressure, or pH, gauge pressure. That rev term is why your ears pop when you dive down.
Makes sense. What about gases, like air in a room?
For gases, the density is much, much lower than liquids. So the change in pressure with height over typical distances, like the height of a room, is usually incredibly small, often small enough that we can just ignore it and assume the pressure is uniform.
Okay. And this pressure in fluids leads to Pascal's law, right? Something about transmitting pressure.
Yes. Pascal's law states that if you apply pressure to a confined fluid, that pressure increase is transmitted equally throughout the entire fluid in all directions.
And that's how a hydraulic jack works. Small push on a small area creates big force on a big area.
Exactly. You apply a small force, F1, to a small piston, area A1. This creates a pressure, PF1A1, in the hydraulic fluid. That same pressure P is transmitted everywhere, including to a larger piston, area A2. Since pressure is the same, the force on the large piston, F2 equals PA2, is much larger because A2 is much larger than A1. It multiplies the force. Clever application.
Very clever.
Yeah.
So how do we actually measure these pressures, especially atmospheric pressure? I know we use a barometer.
Right. Atmospheric pressure, or barometric pressure, is measured with a barometer. The classic design comes from Evangelista Torricelli back in the 17th century. He filled a long glass tube sealed at one end completely with mercury. Then he inverted it into a dish of mercury. The mercury column in the tube dropped, leaving a vacuum at the top, but it didn't drop all the way.
Why did it stop?
It stopped because the weight of the mercury column inside the tube was perfectly balanced by the pressure of the atmosphere pushing down on the surface of the mercury in the dish. The height of that mercury column is a direct measure of atmospheric pressure. Patnam instaural ref, where Ra is the density of mercury. Standard atmospheric pressure supports a column about 760 millimeters or 29.92 inches high.
And you mentioned mercury is super dense. What if Torricelli had used water?
Ah, if he'd used water, which is 13.6 times less dense, the column needed to balance the same atmospheric pressure would have been about 10.3 meters high, over 30 feet. Highly impractical.
Definitely a three-story barometer.
Right. And this atmospheric pressure isn't constant. It changes with weather and altitude. Lower pressure at higher altitudes is why cooking takes longer water boils at a lower temperature. It's why airplanes need longer runways to take off on hot days or at high-altitude airports, and why they cruise high up for better fuel efficiency in the thinner air.
Makes sense. Okay, what about measuring smaller pressure differences, not just atmospheric? You mentioned manometers, those U-shaped tubes.
Yes, manometers are great for measuring small to moderate pressure differences, often relative to atmospheric pressure, gauge pressure. They contain a liquid, often mercury, water, or oil. One end is connected to the pressure you want to measure. The other end might be open to the atmosphere or connected to another pressure point. You measure the difference in the liquid levels, H, in the two arms of the U-tube. That height difference, combined with the density of the manometer fluid and gravity, G, tells you the pressure difference. There are simple rules. Pressure increases as you go down in a fluid column, decreases as you go up. And pressure is the same at any 2 points at the same horizontal level within a continuous stationary fluid. You use these rules to work your way through the manometer fluid levels to find the unknown pressure.
Okay, balancing the fluid columns. And nowadays, we also have fancier electronic devices, right?
Oh, absolutely. While manometers and mechanical gauges like Borden tubes, which use a curved metal tube that tries to straighten under pressure, are still used, modern pressure transducers are very common. These use various electronic principles, strain gauges changing resistance, capacitance changes, piezoelectric effects to convert pressure directly into an electrical signal. They're fast, accurate, and can be easily integrated into control systems. We also use things called deadweight testers for very precise calibration of other pressure gauges.
So quite a range of tools. Okay, we have really covered a lot of ground here in this deep dive into thermodynamics. We started right at the core, defining it as the science of energy, talking about heat and power, and those absolutely crucial first and second laws, conservation versus quality.
And we touched on the history, how it emerged after the machines it explains were already working, and the two ways of looking at it, classical versus statistical.
We demystified the language, dimensions versus units, SI versus English, the whole deal with redefining units based on constants.
Yeah, and untangled those common knots like mass versus weight, power versus energy, stressing dimensional homogeneity. Don't add apples and oranges.
Then we set the stage with systems, surroundings, boundaries, closed versus open systems, properties intensive, extensive, the continuum idea.
Density, specific gravity, all those key properties.
Right. And then the dynamics.
Yeah.
States, equilibrium, thermal, mechanical, phase, chemical. The power of the state postulate needing only two independent intensive properties.
Processes and paths. That ideal quasi-static process. Isothermal, isobaric, isochoric. Cycles. Steady flow.
And finally, temperature. The Zewolf law giving us a basis for measurement. Celsius, Fahrenheit, but crucially, Kelvin and Rankine for absolute calculations.
Finishing up with pressure. Absolute, gauge, vacuum. How it changes with depth, Pascal's law, and how we measure it from Torricelli's barometer to modern transducers. It's a lot, but what's really key, I think, is realizing this isn't just theory for exams. Thermodynamics is literally the engine driving our world. It's in our bodies, our homes, our cars, the power grid, everything. Gaining this understanding, it's not just about facts, it's about building an intuition for how energy behaves, how it flows, how its quality matters. As they say, knowledge is most valuable when you actually understand it and can apply it.
So maybe a final thought for you, the listener. Next time you feel a cool breeze, or you're cooking dinner, or even just thinking about your own body regulating its temperature, go pause for a second. Think about that elegant dance of energy. The conservation? Yes. But also the quality, the direction things naturally flow. How might understanding these basic thermodynamic ideas change how you look at your daily life, or maybe even how you approach bigger challenges related to energy, efficiency, or sustainability? We really encourage you to just observe the world through this new thermodynamic lens. Notice where these principles are quietly, powerfully at play all around you.